Frédéric et son histoire, bien, c'est pas mal de, de commencer par l'histoire des méthodes VOF et en particulier euh, dans les années 90, quand on a commencé à travailler sur les méthodes VOF, c'est il y a très très longtemps, c'était avant même que Stéphane commence sa thèse. Eh bien, on a découvert les premières méthodes qui étaient développées par les National Labs américains. Donc, les méthodes VOF du premier ordre. Ensuite, avec Rubens Cardovelli, Gianluigi Zanetti et d'autres, on a développé des méthodes du second ordre. Et, euh, et à ce moment-là, j'ai rencontré les Californiens, eux, donc Stan Osher et Fedko et d'autres se sont mis aussi beaucoup aux simulations multiphasiques en développant les méthodes de level 7. Et c'est à ce moment-là que j'ai rencontré Osher et Fedko. Et à ce moment-là aussi, à peu près à ce moment-là, je suppose que Frédéric a fait sa thèse avec Stan Osher et ensuite a continué à UCLA et ensuite a continué à Stanford avec Fedko, euh, qui, euh, qui était un de nos concurrents. En fait, avec Jean-Louis Zanetti, on essayait de vendre à l'industrie nos méthodes VOF et en fait, Fedco va essayer de vendre les méthodes Level 7. Je crois que c'est Fedco qui a gagné. Et il a fait tous les films euh, de Hollywood en utilisant des méthodes de simulation pour simuler des gouttes, des vagues. Peut-être que Frédéric, tu étais impliqué là-dedans aussi, hein. En tout cas, maintenant, Frédéric est à l'University of California à Santa Barbara et il est aussi Chief Editor de Journal of Computational Physics et il a donc beaucoup travaillé sur les méthodes Octree, Quadtree, etc. et sur le machine learning. Et donc, on continue à travailler un peu sur les mêmes choses. Et c'est un grand plaisir de t'avoir ici, hein. Donc, je t'en prie, tu peux. You
Thank you
may
very much.
start.
Okay.
And
Okay.
you have your.
So I've got the microphone, so I understand people are online and listen. Okay. So thank you, Stefan, for the introduction. It's a pleasure to be here in Paris, of course. It's a beautiful place. So let me talk a little bit about stuff that we've done. All right. So we use this level set method, which is described here as an example. Just one sec. Right. So if you want to keep track of two bubbles that expand and merge, level set method describes this as a higher dimensional function, and you take a cross section of it, and the change in topology is done automatically. That's the big thing. Now, since it's an implicit approach, the problem is how to impose sharp boundary conditions. And then because you have different of length scales in most of the problems, adaptive merge refinement is something that you will have to do. Stéphane Popinet and Frédéric are doing this as well. And I want to present a little something about machine learning. And on the way, I would present some application in fluids and materials. All right, so usually I present this thing with a two-phase flow. Here you have water that is pushing oil in a porous medium. Because of change of viscosity, you have this viscous fingering that is occurring. And if you look in the bottom, I'm just going to show the grid that is being adapted. All right, so here you have the level set that follows the interface between the water and the oil. And fine grids are going to be put on the interface, which is where most of the physics goes. In terms of adaptivity, imagine that you have a current of water that you let go, splashes around. If you refine according to the vorticity or the norm of the gradient of velocity, you have a grid that is like this. And the zoom here shows that you have very small cells next to larger cells that can occur. And so for this reason, we want to develop methods for general grids, okay, where the ratio between cells is arbitrary. think it's working. All right, so Octree, so of course people are familiar with this here. Octree, the entire cell is the root of the tree, and every time you split into 4 kids, in 2D or 8, you have additional children, additional level, and the advantage of the Octree or Quadtree is the access to the leaf to do discretization is done in log n, so it's fast access. For those who do fluids, it's traditional to use McGrid for good reason. Pressures at the center, velocities at the cell faces, and all the scalar quantity are the nodes. Now, I think the first person who noticed this was John Strain. For the linear advection equation, he pointed out that if you use the method of characteristics, so the solution at the blue point here is going to be dated by copying the value at this point that you obtain by tracing back along the characteristic curve and then interpolating. And if you store things at the nodes, then the interpolation is trivial. If it was something on McGrid at the center, you would have to construct simplices that are difficult. And so we had the idea of trying to figure out if we can generalize the method where things are stored at the nodes, everything is at the node. And here for the main question is what you do when you have cells of different levels, then you have one cell that is missing a node, and it's called a T-junction here. And so the idea is how do you define this ghost node or this new node in such a way that the discretization you're going to do after going to make sense, accurate. The first idea is, of course, to do a linear interpolation of the nodes that you have. And if you do something like this, you can figure out by simple analysis that this value of the ghost node is the exact value that you would have plus O of delta x cube. This is great, third order accuracy, except that you get this nasty term on the way to get the higher order accuracy. But now the beauty when you have when you store things at the node is that if one point is missing in the x direction, then for sure the point in the y direction are aligned. And therefore you can approximate derivatives along the direction very accurately because that becomes regular grid. And that's exactly the point, the thing that you want to get rid of. And so you can define your ghost cell as being this approximation here. The phi yy can be approximated by what you would do, a central differencing, the weighted central differencing. And then you define your ghost cell this way. And if you do something like this, then this one is third order. And it's always possible in a quadtree. Okay, if something is missing one direction, for sure it's aligned in the other one. And once you have that, then you can apply any sort of fine difference that you would use, upwind and central and et cetera, et cetera. It only uses 2 adjacent cells, and this is something that is interesting from the point of view of parallelization. When you parallelize something, getting points that are far away may happen to be on the other process, and communication is extremely expensive. The name of the game is try to minimize those. And so if you just have one neighbor that you need, then it's nice. In 3D, so the formula look a little bit ugly, but it's the same thing, right? Whatever the configuration that you have, you always have 3 points that are aligned. And thanks to those guys, you can correct the error in the transverse direction. And so you can, this is the formula for the those cells. And after that, you use central differencing, fine differences, whatever you want. The advantage you have in adaptive measurement, as you know, is that you have a better resolution. The level set method, for example, is known to lose mass. For example, you have here the same simulation where you start with the disk. You swirl this thing under a velocity field that is incompressible. So when you come back, it should be exactly the same thing, except that that depends on the resolution that you have. If you have very high resolution, you get the original disk. If you don't, then you have that, on the 256 square, you come back with that disk, which is not a disk. Obviously, you've lost all this mass. And if the grid is even coarser, then you lost everything. Okay? So this adaptivity gets you this thing. You can get some loss of mass that is negligible. Same thing in 3D. In 3D, here you have a very thin sheet, and the resolution allows you to conserve that thin sheets. If you had the grid resolution that was less, you would have holes that would start to appear. And so, like I said, you can discretize things the way you would do on uniform grid. And so here's an example where you have where you solve a Stefan problem. No, this one is Poisson, sorry, the Poisson problem, where you have a grid that is completely arbitrary, and you build a system the way you do it, and you get the solution that is second order, and the gradient is second order. And this one is a big deal because in problems like Stefan problem, I'm going to show later, in the Stefan problem where you have an interface that is moving according to a certain velocity, and the velocity depends on the gradient of the solution. So the accuracy of the entire problem is that of the gradient. So keeping the second order gradient is important. Where you win also in those adaptive stuff is when you have a problem that is elliptic or parabolic. So when you have a problem that is elliptic or parabolic, the solution is infinity at t plus epsilon, t0 plus epsilon, right? So you know the solution is going to be smooth. So you know you can accurately capture the solution with a coarse grid, except when the solution has a kink, and the solution has a kink close to the interface, because the solution looks like this, right? You have it's parabolic inside and outside, and it's decoupled by the Dirichlet boundary condition at the interface. So you have a kink. And so it makes sense to put a lot of resolution next to the interface where things happen and coarser elsewhere. And so here's the comparison where you have a uniform grid of 256 squared. And here the effective resolution is just that on the interface. And the accuracy is pretty much the same. Okay, and again, we know that from mathematics, okay? It's parabolic or elliptic, so you get to have that. But since here you have many less degrees of freedom, the linear system is much smaller, and so you solve much faster. So those methods on adaptive image refinement for elliptic and parabolic, they are the winner. There's no contest. Okay? When you add some advection, fluid and stuff like this, that's a different story. So talking about fluid, usually we use a Magritte arrangement, and it goes back from quite a while back. The projection method of Chorin is telling you that any vector field can be decomposed as a divergence-free field plus the gradient of a function, scalar function. Okay, and what you're after is a function that is incompressible, so divergence-free. So you use this decomposition, and you basically have three steps. You have prediction and correction. The correction involves solving a Poisson equation. And the way you should write things would be the divergence of a gradient. That's the operator for the Poisson. Now on the grid, you don't write the divergence of a gradient. If you were to do this, you would have a decoupling between the odd and even numbers and get some oscillation. And so instead of using this thing, you write a Laplace equation. Laplace for the Poisson. So here it's an approximation. It's not an exact projection, it's an approximate one. And so if you use a Magritte arrangement, naturally you have that the gradient, the discrete gradient, is minus transpose of divergence. That's something mathematically, of course, it's correct. But discretely, you will have it automatically on the Magritte. And therefore, you can, at the discrete level, follow the same thing as you would do for L2 stability, and you have that the projection is stable. So Magritte, you will get stability for sure. Okay. Now, when you do this thing on Octree, different ways of doing it. It's people here have done stuff like this. We've done stuff like this. It works. Okay, you get something stable. It's first order accurate though. So we revisited this thing, and So again, this is the crux over there. You have guaranteed stability if you have this relationship. But if you add a node, then suddenly you don't have this thing anymore, right? Instead of solving the divergence of gradient discretely of a function, you have the Laplace of that function. And the projection is to follow the Hodge decomposition, discrete case, to say that the incompressible velocity field is the predicted one, okay, minus the gradient of a certain function. Basically, it's the projection. You have a space of divergence free, and the other one is orthogonal. And the U star is somewhere here, and you want to project it onto the space that is divergence free. But again, this is just an approximation if you do something like this. And if you were to do on a Mach grid, and you were to do the projection again and again, you would get that once you have projected, you're on the right space, and so the solution stays constant. Okay, so this one is correct. In the case of a node base where you don't have this thing, you cannot use this approximation. If you were to do it, then you would have something that after repeated projection goes off the roof, becomes unstable. And so, of course, what you do in practice is just do one projection, but through the course of a simulation, those errors accumulate. They are coming from projection, and it's as if you have something like this. And indeed, it becomes unstable, and more so when there's a high ratio between grid cells. And this is something actually took us a while to notice it, because everything was working. And then we had some little kinks. Sometimes the code was blowing up. And then we got it, that it was a problem of the projection. And so what happens when you do something like this, when you project... okay, thank you. Hola. You also have to be attentive. So the problem is when you have this, this is divergence-free field, and you have U star that lives here. When you project it down, you don't quite make it, right? You sort of go at a little angle, and you don't quite make it to that field. And so one way to impose this thing is to impose that the projection is orthogonal. So it's bizarre to talk about orthogonal projection because projection is orthogonal, but discretely it's not. You want discretely impose that indeed it's orthogonal. And so if you impose that the U star and the gradient of phi as a dot product is equal to 0, then you find that this projection here has to have actually a certain coefficient in front of it, a little something that makes it go exactly on the divergence space. And if you do this, then things are perfectly stable, mathematically stable. And the advantage is don't have a Mach grid anymore. So everything is at the node. And the other advantage is that it's second order accurate. Second order accurate. So here's an example for the driven cavity problem. I think this is for Reynolds of 1,000, comparison with GIA here. And yeah, the divergence is also second order accurate. So when you do this orthogonal projection, it's not the original approximation, okay? So you change a little bit something. And the question is, well, do you change something about the divergence? And it's just a little something. I mean, we looked at those numbers, like 10 to the minus 5 that you have to put in front of the projection. So it doesn't quite make it, but it's very, very close, okay? But it's far enough yet to be unstable. All right. Then the parization of this thing. So there's this work by Burstade, Wilcox, and Gadas. They developed this P4S library that everybody is using pretty much. And so what it does, so communications are bad between processes. Here, different processes have different colors. So what you want to have is to have block of yellow and block of green, so that the communication between processes is minimized. And one way to do this is to use this z-ordering. The z-ordering is, so imagine that this one is a big cell. You would go from here to there, to there, to there. So it looks like a Z. And then, of course, if you have a refinement here, then you do the Z ordering before you go to the next cell. And if you do something like this, then naturally things are by block, like these continuous blocks. So what pForest is doing, it's basically giving you this. It gives you a 1D array where you have, so you number those cells in 1D, and then you divide by the number of processes you have. That's it. And you have the parization that is done in such a way that the partitioning is done properly. You will have load balance. And so in our case, what we do is we have the local grid. So it's the general grid. And then for each process, we reconstruct a local tree in such a way the leaves of our Octree or Quadtree is that of the pForest library. And elsewhere, so if you look at here, let's focus on this red processor here. So the red processor has all the grid points that are needed for what it's responsible of. Okay. Now, to access those points, you need to have a structure of Quadtree. And the structure of Quadtree, for example, in that area, doesn't have all the grid points that the blue process has because it doesn't care about that. It's just to be able to get to the leaves of each element. So that's what you do. You get the array from pForest, and then you reconstruct a local tree in such a way just for you to access element, and then everything I talked about before apply. That's it. So what you get is of course you have parization. So this 3D stuff, you can swirl it around many times. You have very thin sheets. You can capture it. And for problems that are elliptic, I'm interested in crystal growth in 3D printing. The main process is diffusion dominated because you have a lot of components that are allowing element that propagate the fluid. And those type of problems are parabolic. And for parabolic, those things work really well. So this is simulation where you have grains that start to grow, crystals. And then this is a zoom of them. So you see it's a 3D with something that is not trivial. And then you are able to capture the local boundary layer. Here's the thermal boundary layer. Okay. And again, this is a case where you're going to win because it's parabolic. Okay. Same thing here. This is a simulation that I think looks impressive, where you have a well-resolved interface, which is actually just part of this big thing, which is part of those two things, which itself is part of this thing, which itself is part of that, which itself is part of that. So it looks really impressive. But what happens is that, those guys are far away, and when it's far away, you can use very coarse grade. And so on the uniform grid, you would take like 2 to the 20 square, completely impossible. And with this adaptive is, 3 million. So it's 0.5% of the thing. Again, for parabolic stuff, adaptivity is fantastic. For fluids, then here we get, we drop to first order. No, sorry, it's still second order, but there's much more numerical diffusion. Here's an example of gravity current, higher density that's flowing into lower density one. The same thing here in 3D. And then this vortex shading. I don't know if you've seen the picture of dolphins that makes those vortex. When people smoke and they make this thing, dolphins have fun and they make this thing in underwater. And so this is not a dolphin, this is just a flow past a cylinder that is going to have some vortex shading. A little bit about scaling beyond the number of processes that we have available. And then from there, what we do, we do some simulation of fluid flow above some what I call superhydrophobic surfaces. So surfaces where you have grooves and you have air in some part of the groove. And since water slides much easier on the air than on the solid, you can have drag reduction. Okay, there's a whole story about it. It's not just that surfactant has a big effect, but so we can do simulation. So how to impose boundary conditions? So we use this ghost read method, which was invented first for compressible flows. It had nothing to do with imposing boundary condition. It was like when you have a shock wave in compressible flows, numerically you have the solution is O of 1 at the shock. Even if you use like INO or WINO, you have a shock transition. And so the idea was to say, well, it's because of the fact that you have the real fluid on one side of the shock, and on the other side you have a jump condition given by the Rankine-Dugonio, you know that. And when you take a numerical derivative of a function that is discontinuous, you introduce some errors. And so if you want to bypass this kind of error, what you can do is take the real fluid, add the Rankine-Dugonio boundary condition to go up, and now you have something that is smooth. You can take the derivative, and then you subtract back the jump. That was the idea. And so this idea of creating a fluid that is not real, a ghost fluid on the other side of the interface, became a little bit the way of doing boundary condition on level set. And so everything that is done after that is called ghost fluid, even though it's not really the original idea. And so, for example, Dongyu, Fetku, and Minjo Kang solved the Poisson equation with some jump condition. That's something you would have on multi-phase flow. And the way they did it is, so you have the jump in flux that is given by some function. And instead of taking the flux, they took the jump in the derivative, in the gradient. And they did a dimension by dimension approach of this thing. And so basically what they do is they ignore the tangential component of the solution around the interface. And they said in the paper, okay, we know we're making this mistake or this approximation, but we're just interested in the jump in the normal direction, okay? And so if you do something like this, you get a method that is absolutely trivial to implement. The stencil is 5-point stencil, it's symmetric, positive, definite, it has all the good stuff. The problem is that you can only apply it if you have an invested flow and no mass transfer. If you do have that, then the solution actually does not converge. The flux does not converge. And so one thing we did was to say, well, when you write the thing, you ignore the tangential component. So let's put back the tangential component, do all the derivation of the ghost fluid and get some formula, and then you correct that thing. So here's the example. This is a manufacturer solution. You have a jump in solution gradient. The solution is converging, whether you use a ghost fluid or our extension, that's why we call it but the flux, that's the flux of the ghost fluid. The flux just doesn't converge. So you have to do those iteration and add back the tangential component. So if you have, for example, a problem where you have a Marangoni flow, for which the tangential component is important, you have to do this treatment. So here's an example where you have, so this is viscous flow, you have a background of a gradient of surface tension, and if there's an analytical solution, that tells you that you have a kink here at the interface. And so if you take, so this is for two-phase flow, if you take a jump in viscosity that is 0, then the solution is going to converge with 0 iteration. Okay? You don't need to iterate, you go through stuff, no problem. But if you have a jump, then again, ghost fluid is not going to converge, and XGFM will converge. And I have to say that I've seen this thing here used as an example of convergence for two-phase flow, but the mu is always, there's no jump in u. So it's a little bit, one have to be careful. When you have phase change, same thing. So this is a method where you have, a problem where you have a drop that is evaporating, so it's shrinking. And you would have a spurious current. This is something actually that I did in the past using the standard ghost fluid. And so you see inside you have a spurious current. Okay, you should have 0 velocity. And this one, it's actually plotted, okay, but it's really 0. The velocity really is 0, and you have a jump of velocity outside. Okay. When you have phase change, the velocity is increasing. All right, show you a little movie here. So here you have a hot plate and a thin sheet of paper, and your bubble is being formed, there is going up, and process repeats again. You have a very large jump in viscosity and density. What are the things that are interesting? So inside the pressure is constant, and outside you have this quasi-hydrostatic pressure. If you look at the jump in velocity in a region where it's cool, you pretty much have something that is constant. Next to the hot plate, you have a lot of mass transfer. So you can see, you have quite a lot of colors for the discontinuity in normal velocity. So it looks like it's doing okay. How much more time I have, Stefan? Okay, good, perfect. Okay. Okay, all right. So I want to talk about a little something about machine learning, because you have to do machine learning these days, and there's a lot of potential really. So one thing, so we looked at this problem where you have, so basically a Poisson equation. It's almost, but okay, it's a Poisson equation where you have a jump in solution and flux. Okay, can we do something with machine learning? So one type of class of methods, physics-informed machine learning. So PIN is one of them. And so what PIN is doing is, so when you do some machine learning, you let the network learn, and when the network learns, it's going to adjust the weights of the network and do this backpropagation by comparing what the network would predict and the exact solution. Okay, and so the difference between what the network, this function, predicts and the exact solution. And then you also want to regularize this thing by the fact that you know the PDE that you're solving. So this is the idea of PIN. You have a certain network, and then you are going to use automatic differentiation. So automatic differentiation is something that gives you something that is exact. Okay? Automatic differentiation to find the derivatives, and then you put that into the PDE, and that gives you regularization. Now, okay, so you do something like this. And then when you do the backpropagation, you change the weight by finding the gradient of all those weights. Okay, and you do that also by automatic differentiation. Now, the thing with automatic differentiation, I think, is I don't know if it's misunderstood or if it's not looked at the right way, but automatic differentiation is going to give you the exact derivative of the exact function. Now, when the network learns, you don't have the exact function. So it's the exact derivative of a function that is an approximation. And so what you see in effect is when the network learns, the convergence of the spin methods, goes all over the place. Okay, sometimes you have good results, sometimes bad ones, sometimes good results, etc. And I believe this is because of the way those derivatives are approximated in automatic differentiation. The other thing is that this is an example that the student FEDCO did. Automatic differentiation, it's not very smart. So if you give this function, x squared minus 4 of x minus 2, and you find the limit at 2, any high school student is going to say, well, a squared minus b squared, I get rid of x minus 2, and then I find my derivative, right? Automatic differentiation is going to not do that. It's not smart enough. It's going to oscillate near 2. Okay, it's going to plug 2 here and 2 there, 0 over 0, and find something. So it's not very, very clever. And so the idea that we have is, instead of using this automatic differentiation, so we use automatic differentiation for doing this backpropagation like everybody else, but in the regularization, instead of finding the derivatives by automatic differentiation and imposing the PDE, we put the numerics directly. And so that, I think, has a big advantage. First of all, this here does not depend on automatic differentiation. And all the knowledge that you have in numerics on how you impose jump condition, boundary, and all these things, you can stick it there. And so here's an example. So this solver here to impose the jump condition is another one that we derived. Here you have the solution of the error, the gradient, and the condition number. When you do this kind of stuff, so you have a network outside, network inside, and they're linked together by this utilization. There's some leeway on how you define a ghost point on the other side of the interface. You have two types of formulas, and one that I call bias slow or bias fast. Bias slow means you look at the divergence coefficient that is the smallest, and that tells you which formula you have to use. So if you use the bias slow, you see the blue one, you have, so this is for different ratio of mu. The bigger the ratio, the harder it is to solve. You see that the solution error is bounded. It can be very slow if you don't have a jump. Okay, that makes sense. If you have a jump, then the error is more, but it's bounded. If you were to do arbitrary, or if you were to bias fast, you would get something that does explode. As the ratio gets bigger, you get error that are huge. Same thing about condition number. Condition number goes off the roof. But if you do the bias slow, you get a condition number that is actually bounded. When you choose those Gauss cells, it's very important to look at, which formula you're going to use. You have a choice, and you choose the one where D is less. All right, and so here's an example. So for the error, this is the machine learning. As you increase the number of grid cells, you get what you would expect, from numerical point of view. More grid points, you get an error that is smaller. Pin would go, like this all over the place. And it's coming from this automatic differentiation. So here's an example where you have a domain, and inside and outside it's arbitrary, you have a jump, and that's the error that you get. Same thing on the Stanford Dragon. This is the electrostatic field, I guess, around the Dragon. And so I'll refer you to this paper. So the student who wrote this thing was a PhD student who went to NVIDIA after, and so he had access to all those GPUs, and he did all those tests. That's a lot of work. That was not. Okay. Time for more, yeah. Time for more. So this is something that actually those two guys have done. It's for an application of fluid in the porous medium. So it's single-phase fluid, but the porous medium can have precipitation of dissolution. So the interface is ring. I'm sorry about this thing here. It doesn't render very well. But basically what you have two scales. You have the scale of the fluid flow, and you have the scale of how fast the interface is growing because of precipitation. And the precipitation, of course, is much, much slower than that of the fluid. So you think about, okay, you're going to use a quasi-static approach. And the question is, how many time steps can I do for the evolution of boundary of the precipitate compared to that of a fluid flow? And you assume that the fluid flow is basically constant when the geometry is pretty much constant. And how long can you do that? So, if the geometry changes a lot, for sure it's going to change the fluid flow, but how much is a lot, right? So this analysis here is to try to figure out what is the difference of those delta T, and the quantity of interest are going to be the area of the grain, 2D, it's the perimeter, the reaction rate, which is this thing, and the outlet flow rate. And so, okay, we did some simulation, or they did some simulations, and compared to other work. And basically, that's basically what you have. You can go about 100 times faster simulation for this type of problem here with a quasi-static. For this one here, so it depends on a lot of the different parameters that characterize this problem. So it's the Damoclean number and the Schmidt number. This is an example where you have a certain porous media, you have a gradient of pressure along this direction, and the precipitate grows. Same thing, we're going to look at the tortuosity, the porosity, and the mean interface velocity. And so depending on the type of regime, so if you have a high regime, you can do about 10 interface solves per Navier-Stokes. This is when the precipitate grows rapidly. So you have the chemical reaction at the precipitate. But then for regime that are medium or large, then you get a lot, 200 for medium regime. And if something are very slow, you can get 10,000 interface evolution. So for 10,000 steps, you don't solve Navier-Stokes, which is, of course, again, they would be impossible otherwise. All right, analysis about the merging. As you refine the grid, the merging of two grains is converging. You can see here where they meet. You have, if you take two grains, so here there was to see if you get the Poiseuille profile. So two grains are growing and eventually merging. The velocity here along the direction that join the two center of masses is like this. If you scale by the maximum distance between the grains and the maximum velocity, they fall under one stimuli solution. And then after that, you can play some games. So you have, depending on the Damoclean number and the Schmidt number, you have different type of flow. The precipitate is going to go a certain way. And you can see the profile of velocity here. If the fluid has come, this way, and you have a parabolic profile, then it goes this way, so the parabolic profile. But then here, it starts to turn around, and the profile is something completely different. You really need the stimulation to be able to try to get something out of it. And what you want to get out of it is this effective permeability. Okay, if you have, for Darcy law, you have a certain formula that relates the flow rate to the gradient of pressure. If you have a multi-phase flow, or if you have a domain that is changing in time, Darcy is not working. And so the idea would be to find an effective permeability. This kind of work. All right, so here's an example for the permeability. Kind of high at the beginning, and then it goes down because, of course, things get clogged. And I think I will leave it here. Okay, we've done this thing for precipitation, dissolution, something also for ice comparison, some experiments. I think I will leave it here. From the what? Yeah. Yeah, it really is. Yeah. Yeah, no, it's plotted. It's just too small to see. That's normal because when things vaporize, you have a jump in velocity, right? The density out, density is less, so it's mass transfer, exactly. Yeah. No, actually, it's much better. You cannot. I mean that's the thing. People have talked a lot about the interpretability of the network, saying that we don't get the result we would hope for, but that's because we don't take enough layers or not enough neurons, something like this. But it really is a question of automatic differentiation, because here I think we used was just 1,000 neurons, just one layer with or 100 neurons, something very small. Yeah.
Thank you for the presentation. So I didn't quite get, I don't know if you could explain again, the spirit of the correction when you do the projection, and you said that the projection is not exactly orthogonal.
Yes. This one here?
Yeah.
Yeah, so this guy here, when you do minus the gradient, so if you were to solve this equation exactly, right? So discretization of the divergence of the gradient, okay? Then that gradient here in this formula would be good, okay? Now, if you do something like this, you get this problem of odd even decoupling.
Mm-hmm.
So instead of that, you use Laplace. So the solution that you get now of Laplace, which has some error, when you compute the gradient, you don't get this one. You get something that's a little bit different. This gradient here is a little bit different. The gradient of E tilde is not the one that you would like to have. Okay? And so since you make a little error here, you need to correct it. And one way to correct it is to say, well, I want to impose my projections orthogonal, and that's going to give me the correction term. Right?
Thank you.
Yeah. That's why I wrote, this here, DG, these are the discrete operator. Mathematically, were to do it by hand, this and that would be exactly the same, right? But numerically, you make some mistake, and you have to correct it somehow. Yes. Yeah. I mean, I think your interpretation also is correct, right? I mean, different ways of seeing it. Yeah.
So whenever you use the pin networks, this is to solve steady or unsteady problems?
It's steady.
Steady, okay.
I mean, the big question is what you do when your interface is moving. I think the person who solves that in machine learning is going to be famous.
Uh-huh.
Yeah. So here again, yeah, I mean, so this is a good point. What's the point of machine learning here for something like this? I solve this thing. Wonderful. 1 millisecond to evaluate, 1 week to train. Okay, we can do that numerically all the ways, right? What's the point of doing this? Well, here the point would be if I want to do this simulation for different value, for example, of diffusion constant or whatever, I want to do a million of them. Then now I can do one after the other very fast. So my training was worth it. Otherwise, what's the point? I don't quite know, right? So when you have a domain that is fixed, yeah, you gain something. But when you have something that is moving, you cannot do a week of learning for each, interface to then run something, and then, even that wouldn't work, right?
Thank you.
So yeah, yeah.
No, thanks. So basically, you use, I think, the velocity to train the model as the data.
Yeah.
Is that correct? Well, my question would be, how could you address the non-Galilean invariance of the velocity? So if you change your reference frame or the geometry, and you still want to use your network to predict your field.
So you mean at time of evaluation or training?
No, evaluation, not training. For example, if I train the model in a certain reference frame.
Well, you would have to work it out in that term, right? This is where you impose whatever you have.
Yeah.
Yeah. Yeah. How exactly, I don't know, but
okay.
This is where you would put it. Yeah.
Okay.
And then there's also something that is quite recent. I don't know if you heard about this Clifford algebra. So Clifford algebra allows you to do something like this. It's to impose symmetries and stuff like this. So this is more when you, when each neuron talks to the next neuron. It's at this level that you can impose symmetries. I'm not well versed about it, but I read a little bit. Okay, thank you very much.